Hello students, this lecture is about ray optics and mirrors and lenses. So let's start with basic definitions, that some of which we have already learnt in class 10th. So let's start with some of the properties. We will study reflection of light, spherical mirrors, concave and convex mirrors, ray diagrams, and mirror formula and numericals we will do in the next lecture. Okay, so let's go ahead and do this. Rectilinear propagation of light. We know that light travels in a straight line, and this property is known as rectilinear propagation of light. The image also justifies the same. Light is traveling in a straight line like this. Now, ray of light, a line drawn in the direction of light, is known as the ray of light. This is a ray of light. A beam of light, it's a bundle of many rays, as you can see. Now, these are parallel rays. These are converging rays because they are going to converge at a point. Convergent beam. And this beam is divergent beam. They are moving away from a point. Reflection of light, we know that there are certain properties. This is known as incident light and this is known as reflected light, and we draw a normal here. This is known as angle of incidence. This is known as angle of reflection. So let's quickly refresh the laws. Law says that the incident ray, the normal at the mirror and the point of incidence, they lie in the same plane. That means incident ray, normal and reflected ray, they all lie in the same plane. Also it says that R equal to I, that means angle of incidence is equal to angle of reflection. So this is what we studied in class 10th. Also let's talk about plane mirrors. Plane mirrors has this very important and peculiar property called lateral inversion. So ABC appears like this. It appears laterally inverted. Spherical mirrors. So we will study spherical mirrors in this topic. Spherical mirrors are of two types, concave and convex. This is a concave mirror. As you can see, the outer region is actually non-reflecting region. The inner region here, as you can see, this is the reflecting region. So reflection will happen from the left face of the mirror. Okay, so why is it called concave? Because it is curving outward. Okay, this is converging and this is diverging. Now some of the common terms that we have to see. If this mirror is a part of a sphere, that sphere will have a center. That center is known as center of curvature. And then there is the radius of curvature. Then there also is pole. Pole is the center of the mirror. This is called pole P, as you can see here. And if you join C and P, you will get principal axis. And let's talk about the term aperture. The effective area of mirror available for reflection is known as aperture. So the bigger the size of the mirror, the more will be the aperture. So you can talk in terms of some example also. We know that the lenses inside smartphone cameras have smaller aperture, but if you consider a DSLR, the DSLR camera has a larger aperture. So because the effective area through which light can enter is large in a DSLR. Concave mirror, as you can see, it's a converging mirror. Do you see all the parallel light coming and focusing at a central point? This point is known as focus, and the distance from pole is known as focal length. So if you look at this diagram very carefully, you can see that this is the focal length. Pole to focus is known as focal length. And as you can see here in convex mirror, parallel rays after reflection converge or appear to diverge from its principal focus. So we know here that r is equal to 2f, double of focal length, so focal length will be half of radius of curvature. So we can prove this, and we can have a look and just prove it. So we will prove it f r is equal to 2f with the help of this diagram. As you can see, this is the pole, this is focus, and this is center of curvature. A parallel ray striking at M after reflection passes through focus, because any ray which is parallel to principal axis will always pass through focus. Now there are two kinds of rays. One is known as the paraxial ray, the other is known as marginal ray. So paraxial rays are those rays for which M is very close to P. That means they strike the mirror very close to the pole. So in all the derivations that we will do in this chapter, we will consider only paraxial rays. So for a paraxial rays, this is a very important property, that all the angles involved are very small. So if the angle is small, we can say that sine theta or tan theta or theta would be the same, right? So let us see how this happens. Sine theta is approximately equal to tan theta is approximately equal to theta if theta is small. This is a mathematical fact. Okay, so probably we will do the proof of r is equal to 2f in the next lecture. So see you there.